Hi, year 13. Welcome to simple harmonic motion number 5. Get yourself comfortable. Could take a while. This thing here is the pendulum that you saw earlier in one of the earlier videos. It swings backwards and forwards. It describes simple harmonic motion. Why? Because when it's here, there is a component of the tension force in the string, which is horizontal. There's also a component in the string which is vertical, which is equal and opposite to the weight force. Because there is a horizontal component, it accelerates horizontally. When it is hanging vertically, the weight force is balanced by the tension force on the string. Easy. So, for small angles, and I mean small angles, it actually demonstrates simple harmonic motion. I'm not going into the details of why that is at the moment. At large angles, it's not actually simple harmonic motion because the angle's too big, and it's to do with the way that sine and cos work together when they're at small angles. So, what we had is we had a wheel spinning like so, and it had a little bob sticking on it. It had a little thing sticking up like this, and we had a pendulum swinging. Now the pendulum was swinging this way up and down. I could have done it with a spring, but I actually did it with a pendulum. And we had a wheel with a bob on it. Now you need to imagine that the light, which was sunlight, lovely, I got it to work quite well. The light is going that way, all right? There's lots of light going that way. That means that the shadow, which could be on these lines here, would be what we're looking at. So we looked at the shadow from the pendulum, which was going like this, and we looked at the shadow of the bob on the wheel, which was going around the circle. But the shadows matched each other, which is awesome. And I also showed you the one with the pendulum and the sand coming out, and you could see it was a sine graph. So now we're going to look at why it is the sine graph. So if we draw a circle, now this thing here is called a reference circle. So this is a reference circle. Reference circles, by convention, go anti-clockwise. So they always go anti-clockwise. Anti-clockwise. Right? So we're always going to go that way around. We're measuring in radians. Yes, 2 pi radians to a circle, or pi radians to half, or half pi for a quarter for a 90 degree. All right, so when we're looking at this, the bob, our little pendulum, went from the equilibrium position to this, position P. Position P is also position P here. Now the reason we use the reference circle is because it makes the maths a lot easier to understand, and we can then deal with rotational notations on a reference circle. So then the formulas make sense and it all works. So what have we else we got on here? So y on the reference, because y here is the displacement, right? It's in meters. It's just how far did it move from the equilibrium position. Y on here is that little bit of the triangle. The arrow here, which I've labelled A, is called the displacement phasor. So that thing there, A equals the displacement phasor. So what is it? It's an arrow that goes around the circle. It represents what the displacement's doing. When it is here, so if it was here, then it is the amplitude. Why? Because the amplitude is the maximum displacement. So at this position here, A would equal Y, because Y would be there as well, wouldn't it? So at the maximum amplitude, y equals a. We can write that here as well. At max amplitude, y equals a. Okay. What else can you say? So theta here in radians is the angle on the reference circle from the equilibrium position. Now when you get further into this, you can actually draw other things on here to help you, because you already know that half of this is pi radians. So if you had drawn something down here and labelled it, you can still work it out. It's all good. Alright, so you've got y here, that's the displacement. You've got p, that's the position we're currently at. And you've got the rotating phasor there, which we've labelled A because it's the amplitude. And we were looking at the shadow here, and they matched each other on the screen. You can see the previous video for that. Now, when you start looking at some of the maths of this, well, you should be able to read that. Hold on. Maybe that's better. Right, so when you look at the maths of this, the sine of an angle is the opposite over the hypotenuse. Sine of the angle on this triangle here is y over a. Rearrange it and you get a sine theta equals y. Put it the right way around, you get that. That's easy. However, there's all this business that happened before. Velocity in a linear sense is displacement over time, or rotational motion. Angular velocity is angular displacement over time. So it's the same equation, just in rotation. If you rearrange that, you get theta in radians equals the angular velocity, which is radians per second, times time. You can substitute that into your equation, your equation here for theta, and you get y equals a sine theta t. That's the equation on the sheet. That is where it came from. It's useful to know where equations come from, because you have a much better understanding of it. So the next thing we're going to look at on the next video will be velocity, and we'll be doing another reference circle. And then we need to look at acceleration. We're going to need to draw some graphs to show how they relate to each other as well. Thanks for listening. Any questions, let me know.